Let's see. The first thing is that I made a mistake in both the last lecture and the lecture before it regarding these cancellation lemmas, like how you prove that if you have a single gradient flow line from one critical point to another, you can cancel, or the analog, if you in one parameter family, if you see that swallowtail, that you can then cancel it. And so, I mean, the statement's correct, but here's what's wrong with my proof. Okay, and you can see how to fix it up. So let's go back to how to cancel. So correction. Canceling critical points. So what I said is, okay, you've got your two critical points, Q and P, and you've got your single gradient flow line from one to the other. So then I say, okay, now go to a coordinate neighborhood of Q, find the direction that this this descending flow line comes in, and then go out the other direction and go at least below P, and then do the same thing at P, find the direction this comes in, and go out the other side of the same direction and go up past Q. So then you split it into a single one-dimensional direction, and we call it, and then I sort of want to coordinatize this direction as xk plus 1, right? And then you split off a descending and ascending directions all the way along this arc. So I think of this as an arc embedded in the manifold, and you split off ascending and descending directions, and then your descending directions are going to be x1 up to xk, and your ascending directions here are going to be xk plus 2 up to xn, right? And then, so I claim that in a tubular neighborhood of this arc, let's call this arc A, and then you find a neighborhood nu of A, and inside this neighborhood nu, you can find coordinates x1 up to xn, so that everything looks standard. And standard is going to mean that f equals minus x squared minus minus xk squared, and then plus the cubic that you see in the k plus 1, in the xk plus 1 coordinate, xk plus 1 minus xk plus 1. That's the cubic part that gives this thing. That's the cubic part that does have two critical points. And then plus the remaining xk plus 2 plus squared plus xn squared. Okay, that much is correct, that you can find such a coordinate system in a tubular neighborhood. And the argument that I sketched is basically right. The point is, you can find those coordinates here, and you can find those coordinates here, and well, down here it's going to look like the xk factor you're going to see is going to look like xk plus 1 squared. Here it's going to look like minus xk plus 1 squared. But then there's sort of, you can interpolate between them, because along this arc it's going to look like a cubic, right? And everything's fine so far. But then I said, now just put a t here, so that as, or a minus t or something, so that as t varies from negative to positive, you cancel this. So I would replace this with xk plus 1 cubed plus t xk plus 1. Now, there's a couple of problems with that. This is a polynomial, right? So polynomials do not, their behavior is not supported inside compact sets. And what I really ought to be doing is I ought to be describing a local modification. I ought to be describing something that happens inside a compact neighborhood, and I don't modify things in the rest of the manifold, because I have no idea what's going on in the rest of the manifold. Okay. So, polynomials are harmonic. They're determined by the Taylor series. They are not bump functions by any means. Okay. I mean, it's polynomial in T and everything. So, so this is a bad thing to just say blithely, okay, do what this polynomial does. What you should really do is do this, but cut it off with a bump function. Okay? And that's sort of what I meant to say. Now, so we should really cut off with a bump function. But then you have to be super careful when you start cutting off things with bump functions and saying something about critical points. Because bump functions can produce new critical points. That's the point. You start multiplying something by a bump function, you can conceivably produce new critical points. And in fact, if you did what I said here, you might. And so here's what, so I'm going to try to draw a slightly more sophisticated picture of that. So suppose I look at the full descending manifold. Let's look at this, and then I look at this. So we only need to go to a surface to start to see the problem with my argument. So suppose I'm trying to cancel an index 1 and an index 2 critical point. What I wanted to do is to do everything inside a neighborhood of this curve here. So I want to cancel inside a neighborhood of that curve here, which means I'm imagining I've got this mountain and then the saddle below, and I'm imagining just taking that green curve and pulling it tight. What's that going to do to this mountain? Well, it's just going to cut it in half. And I'm going to get 2 mountains there, right? I'm going to end up with 2 index 2 critical points on either side. And that's obviously what you don't want to do, right? You don't want to create more critical points. What you want to do is push the whole mountain down and cancel it into this saddle, right? And so you actually really have to be more sophisticated than that. And you have to take the entire descending manifold. And you can choose whether you want to work in the descent, whether you want to push the mountain down or lift the saddle up and make a choice either way, right? But you need to work in the entire descending manifold for Q down to level P. And you'll still have the same coordinate system. Once you get into that a large enough, I mean, you can do it, the best way to do it, I think, is to take the thing is, you know exactly how both the descending manifold and the ascending manifold for P and Q intersect, right? And you really want to show you, I'm not going to give you all the details, I'm giving you far from the details, they're easy to figure it out a little bit, but you really need to work in a neighborhood of the sort of the descending manifold for Q union the ascending manifold for P. You can do various things. You can just work in a small neighborhood of P, sort of tacked onto this full descending manifold for Q, right? And I guess hidden behind all of that is the claim that if you take, and this goes back to describing things as handles, we know how to get nice little Morse, well, we don't have to show you yet, I will show you how to get nice little Morse local coordinates near this point Q. I claim that actually, if you take the entire descending manifold, as long as you don't run into another critical point, you can find the same model, sum of squares, along that entire descending manifold. So you think in one direction a small amount, and leave the other direction big, and that's what I said how you get a handle decomposition by flowing all the way down the descending manifold. That's all I want to say about it. I think the argument is salvageable, but I didn't. So the same thing happens, when I was working with canceling the swallowtail. I said, well, you see this, which means you have 2 critical points, Q and P, Q1 and say Q2, which are both canceling the critical point P. And so you want to sort of, and you want to argue that then you can get, well, more that's sort of at this time here, they're both canceling them on the left, one of them cancels on the right, the other one cancels. So I said, well, really you have this little movie where you start with your, you have a little, yeah, that's right. Start with a single map, then you go to this, then you go to the same height, then you go to this, then you go to that. And since that's all you see in one dimension, you then just work in a tubular neighborhood of that arc and do and modify this in the way we talked about before, and it'll all just work out. But of course, again, that's too simplistic, because you'll be doing the same thing. If you try to just do something in the neighborhood of that arc, doesn't quite work out. So I'm not going to try to clean that argument up any better than that, except to say that the same thing has to happen in this case. I think really where this is written down probably is in Serif's original article, but I haven't looked at it recently to know for sure. Okay, so I may say more later about cleaning those arguments up better, but the other the other thing I wanted to say is that actually, let me draw that same. I sort of had a movie of movies before. I'll draw it again. We start with this, 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 and this, and we wanted to homotope that homotopy so as to get rid of all the critical points, right? So we wanted to imagine some homotopy where in the middle we have a fourth degree polynomial somehow. Here we have sort of a cubic, and then it goes up, and here we have a cubic that goes down like that, right? And so I just want to emphasize that actually you can very quickly write. I think I spoke last time as if it was sort of a mystery how to pull out the local model for this this homotopy of homotopies, but it's not at all, right? So you know that in the middle you've got to have an x to the 4. Right? And now you know that let's pick which directions. We're gonna have two parameters, an s and a t parameter. Let's say this is t and this is s. Let's say I want s going this way, for example. Okay, so the point is in one direction we're going to add a quadratic or subtract. Well, we're gonna take this, which is I've got a minus x to the 4th electron. Okay, that's what it looks like in the middle. So in one direction we're going to add x squared. So let's say as t grows, we want to add x squared. So as s grows, so plus sx squared. Okay, and then in going as, let's say this is going to be t equals 0, and this should be s equals 0. And then in the other direction, we're going to, let's see, when t is negative, we want to be adding, we're tilting, we're adding a linear component, right? So we tilt it off to the side. So I guess I would do minus tx. So that two-parameter family of functions should give exactly this model. Again, it's a subtle thing how to how to cut that off with a bump function and not add Euclid. Right? And that's something that maybe you think about when now I want to give an exercise. Homework problem. I'm giving an exercise in a while. So. This is of more topological nature, it's analytic. So suppose I have a so let's consider a Morse function on a 3-manifold. So closed, so I'm going to map to R. And it has x is closed, and f has 1 index 0 and 1 index 3. Points. And then we know it has, by what we've seen before, we know it has the same number of index 1 and 2 points, okay? And g index 1 is 2 critical points. So now let's choose a metric, choose a gradient like vector field. So that ascending and descending manifolds transversely. Okay, the other thing I may not have emphasized in the cancellation lemma, if you have a single flow line, you need to assume that you've got all the transversality in it. Because if you have, I can have a, this is just, I'll come back to the exercise in a second, but I could have a one handle like this, and then I could have a two handle, and here's the ascending manifold for the index 1 critical point. And I could have a two handle that comes, whose attaching map does something like that. attaching sphere and hits it at one point. So that would be the descending manifold, the ascending manifold intersecting at one point in the intermediate level set, with therefore a single flow line. But this is not a transverse point of intersection. And this is really 0 or 2, right? And so you shouldn't have a cancellation here. And so that should be sort of clear in the proof of the cancellation limit that you use that transversality, you really need that intersection to be transverse. Okay. Okay, so suppose these intersect transversely. Now I'm going to define a, so there's a definition, a canceling pairing. This is just my own terminology. It actually has another standard terminology, but named in a second, which is less revealing. A canceling pairing is a collection of G flow lines. Let's call the flow lines L1 up to G, L1 up to LG, G flow lines for V, between, they're going to go from index 2 to index 1. Index 2 to index 1 critical points. I could just say they're disjoint, i.e., so pairing distinct critical points. So in other words, I don't have a single, two different index 2 critical points coming down to the same index 1 critical point. So it's just some way to pair off the index 2s with the index 1s using gradient flow lines. And there may be many of them. Okay, but the thing to prove is that if there is only one canceling pairing. The reason I call it canceling, so I think of each flow line as a good way to think of a flow line from index 2 to index 1 is a potential cancellation of those two critical points. However, it might not be a cancellation because there may be lots of other flow lines between them as well, and that's a problem, right? But if there is only one canceling pairing, then you can cancel all index 1 points. And of course, you can cancel them all, therefore, x minus 3. So the thing is, there may be 10,000 flow lines between them, but only one way to pull out of, you've got zillions of flow, you can sort of just think of a graph, right? There's a graph behind here. You've got your index 2 critical points. You've got your index 1 critical point. You may have zillions and zillions of flow lines, right? But for some reason, combinatorially, there's only one way to pull out, so this may be a good, right? So here, even though there's, you know, the only, well, this is not, doesn't have zillions and zillions, but I've only got this, 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 and this. I can't do anything else. Because this has to be paired with that one. There's only one flowing into it, right? And once I know that that has to be paired with that, then this can't be paired with this or this, so this has to be paired with it, and then that leaves only this and this to be paired off, for example.
And the last, you need also the last one to be paired with these like that.
That's right, the last one could have started at that end as well, right? And but I could have had maybe this, and it still would be choice.
But if you,
oh, no, that wouldn't, anyway, you can figure it out. It's complicated combinatorially, conditions under which this may or may not happen, but that's the point, that if there's only one possible way, so there's lots of other, and it may be that each individual pair of two critical points has lots of flow lines between them, but still, for some combinatorial reason, there's only one way that you can think about that. So it's partly a combinatorial and partly geometric argument. But this is, now I'll tell you what the more standard and much less revealing name for a canceling pairing is a generator of Hagar-Floyd homology. Like, if you don't never heard of Hagar-Floor homology, that's not helpful at all. If you have heard of Hagar-Floor homology, it's a, well, if you haven't heard of it, it's a particular invariant of three manifolds that is constructed using Hagar diagrams, and it's a chain complex with a boundary map and so on, but it's not standard homology at all. And the generators are precisely these things. They usually say something very different. They usually say, if you look at the Hagar diagram, you've got your alpha curves and your beta curves. Remember, the alpha curves are the ascending circles for the index 1 critical point. The beta curves are the descending circles for the index 2 critical points, right? And they say you've got G alpha curves and G beta curves, and the Hagar-Floor generator is a G tuple of points, where each point is on a G tuple of intersection points. Each point is on an alpha curve and a beta curve, and each alpha curve has one of the points, and each beta curve has one of the points. And that's exactly the same thing as this, because the intersection between the ascending and descending spheres is precisely a flow line from one to the other. And so I like to think about, this is just my philosophy of Hagar-Floor homology. Hagar-Floor has these things as generators. And the idea is somehow if you could cancel these canceling pairings in pairs, so that then you got down to only one, then it would be S3. And so this homology, in my sort of naive understanding of it, is that it's sort of is an obstruction to the manifold being S3. It's an obstruction to being able to cancel off all of these canceling pairings and get down to just one. Okay. So that's just if you go on and learn something about Hagar-Floor homology, maybe that'll help. Now, the next thing I wanted to summarize our corollaries of. So the thing that I claimed to prove last time was that you can get rid of all, if you start out with a, if you have a three-manifold cobordism from, it's connected three-manifold from something non-empty to something else non-empty, and you have we proved that you can have a Morse function on it with no index 0 or 3 critical points, and if you have two of those, you can get between them without adding index 0 or index 3 critical points. That was the main point of last lecture. And so the conclusion now, if you have a closed three-manifold, you can take out two balls, apply this, and then put the balls back in, and therefore you can say that, first of all, so we already showed that there exist Hagar splittings on three manifolds by saying you can find a Morse function on a three manifold with only an index 0 and one index 0 and one index 3 critical point. And now if you have any two Hagar diagrams describing actually I'm just going to say diffeomorphic three manifolds. Are related by handle slides and let's see, but I wanted to say what those are carefully in terms of so these are handle slides and birth deaths, and so these are going to be in the Hagar splitting world, which means we're not going to. So if I had a birth or death of a 0-1 pair, I would be leaving the world of Hagar splitting. So Hagar splitting requires a single index 0 critical point and a single index 3 critical point. If I have two index 0 critical points, then suddenly my handle body is going to be much more complicated. So I want
Births and deaths change.
They're going to change the genus, and they're going to change the surface, yes. So we're going to see what those look like carefully. So now this is the one thing that's a little bit so yeah, births and deaths may be a little easier to describe. So births curves. The Hagar diagram now is we're drawing the surface in between the index 0 and the index 1 and the index 2 critical points. And so we can put on it red and blue curves for, well, the typical thing is to draw it so that the ascending circles for the index 1 critical points are standard in some sense. And you can always, it's another thing to think about, that you can always put them to a standard position. But that's not so important. You don't have to draw that if you don't like to, and then I'll just say it again, kind of simple. This turns out just to be S3. Actually, this is a good example of, this is a very trivial example of an exercise, because there's only one way to pair these guys off, right? This one, and that one, right? And then that, according to the theorem, these would all cancel off. But we also see here exactly a pair that cancels, right? And so as soon as you see a pair that cancels, that tells you what a birth looks like. A birth would be adding, actually, a death is removing this. Maybe I should just draw it that way. So this is birth and this is death. How about that? So this is so death we sort of already understand in the sense but the point is you really should be able to see this as, if I actually think of this solid, so what is this solid handle body really? It's really a 0 handle, and then I've attached 2 1 handles to it. There's the red curves and those 2 1 handles, right? The belt spheres or the ascending spheres for those 2 index 1 critical points. And now I'm going to add a single, I'm going to do something that creates a new index 1 critical point and a new index 2 critical point whose descending sphere goes over at once, right? Intersects at once, and that's the sort of clear there's only one way to do it, but you can actually see. So you add this on. So right there in a small neighborhood, you add the index 1 critical point, and right away you have the canceling index 2 critical point that goes right over it. And there's the 2. Okay. So that's why it's always good. So it's just taking your Hagar diagram anywhere you want in a small disk, you put on this picture. Okay. And then if you see, but also if you see 2 curves that intersect at one point, you should be able to redraw your picture so that they look just like that, and then you just cut it off. Okay, so that's birth and death. And then handle slides, we can also illustrate with this picture. I've already done it many times, but it's so we understand what handle slides with the 2 handles are, but just to remind you. So in this case, if I was going to slide, I could slide that over there, and I would get to draw it. That, and that's I just slid the big one over the small one, and I've got a pair of pants in between, but anyway, then that simplifies. Now, the one thing that's funny is you can also do this. So that was from here to there, the handle slide. The thing that's funny about it is you can also do it with the red curves. And you might think that's weird because you're sliding, I said you should slide 1 handles over each other like this, right? This is a slide happening, we're looking at the slide upside down. When I say slide the red curves over each other, you're really looking at really what you're doing, so if a one handle slides over like this, what really happens is upside down, the one handles are two handles, and this is sliding over that, so upside down, the other one's sliding over, they're upside down. So this is really, these are the one handle slides upside down. And you do have to consider those as well. But they turn out to be just the same, well, they become two handle slides when you turn them upside down, that's all there is to say. So those are the moves. You take the, if I have a picture like that that describes a three manifold, you are allowed to do bursts or deaths, which in three manifold world are often called stabilizations and destabilizations. Okay. So adding one of these is called stabilization. Death is destabilizing. And then you're allowed to slide these things. Of course, there's isotopy as well. You just move them around by isotopies, and you can do handle slides. By the way, moving around by isotopies can be important as well, because you're allowed, for example, to take this blue curve and move it around. That's something. That incidentally is another kind of, there will be a time when there's some non-transversality of SNEs.
So this is probably too much to ask for, but if you have two genus G surfaces, do you necessarily, might you have to add births and deaths?
Yes. Yes. And so an interesting question is, given two Hagride splittings that you know and love of a given three manifold, what's, they're presumably low genus, how many stabilizations would you expect to need to do in between? And that's something only recently people have been able to. For a long time there was a for a long time no one knew any examples where you didn't need to go any more than one higher. I mean, they might have different genus. This might be genus 2 and this might be genus 7. For a long time no one knew any examples where you didn't need to go up any higher, where you need to go any higher than 8. There were examples where you had to go one higher, right, than the larger of the two genes, generally. But some people have recently figured out how to construct examples where you need to go arbitrarily high. They're very small genus, but you need to go arbitrarily high. I don't know the state of the art with that. And an interesting set of examples is where the two Hagride splittings just come from taking the Morse function f and minus f. And there are examples where you take f and minus f, and they're both genus G's. They're actually the same splitting, it's just you've switched red and blue. But to get between them, you have to go, arbitrarily high, or at least twice. I think the examples go to twice the genus. I'm not sure. That's an interesting question. But actually, the same corollary, is worth mentioning in higher dimensions as well. Also, we can't say it in terms of Hagride splittings, but so maybe two Hamel diagrams. I'm just really mentioning. I'm just going to put together two things we said before. Any two Hamel diagrams of a fixed n manifold are related, fixed connected n manifold are related by births, deaths, and Hamel slides. We already said that, but I'm just going to say without mu zero handles or n handles. And this in particular is used quite frequently in understanding four manifolds. So people are able to play around with four manifolds and actually work with handle diagrams of four manifolds. And it's important to know you don't ever have to worry about adding new extraneous zero handles or four handles. Okay. So this thing is called, this is called the Meister Singer. I don't know any of the history really. This is the one that I was saying So there's a preprint on the archive by Laudenbach that I think gives exactly this argument carefully. And I think the point was just that it hadn't been written, it wasn't really written down anywhere. So if you want more precision than I've given, you should put that preprint. Okay. So that's one way to work with three manifolds, to draw Hagar diagrams. I want to now use the Hagar diagrams to give another way, to lead up to another way to describe three manifolds by surgery. And so the next thing I want to prove is every closed X3, actually I'm going to start calling it, I'm going to call it M3 now. M is usually my boundary of something, so if I call something M, it's going to indicate its boundary is boundary X4 or some X4, which equals a 0 handle union some 2 handles. So in other words, first of all, it's the boundary of a 4 manifold. Secondly, that 4 manifold can actually be chosen so it doesn't have any 1 handles or 3 handles in it. It's pretty clear it wouldn't need to have any closed connected. So, no 1 handles. And what's really going to happen is we're going to use the Hagar splitting that we already know to actually construct this 4 manifold. And this theorem is due to English. And the original paper is very beautiful and very readable, and it's called a Combinatorial Presentation, Combinatorial Presentation of Orientable three manifolds. And I think it's true without putting, I guess I need, closed connected oriented. You're never going to get an unorientable 3 manifold if you don't use 1 handle C process.
But is that because of I'll figure it out a little bit.
It's just that the surgery, so remember, okay, what's the boundary of 0 handle? It's S3, right? Now, when you attach a 2 handle, you're doing surgery along a knot. And that, remember, you're attaching the 2 handle along an S1, thickened up, and that means you got an S1 cross B3, you're covering up that S1 cross B3, that no longer becomes the boundary of the 4 manifold, and the new boundary is S1 cross B2, and the new boundary is a B2 cross S1 that replaces it in some sense, which is called surgery, but that surgery just doesn't change the orientation. It just can't. And so, the orientation always extends across things. So it's really because to get an unorientable 4 manifold, the only place you get non-orientability in building manifolds with handles is with the 1 handles.
So I guess I was thinking, if you don't have 1 handles, you haven't changed by 0. So dually.
I guess that's right. I see what you're saying. Yes. Okay. In particular, this 4 manifold is always simply connected, which might be of use and interest. Okay. So the proof of this is. So, start with Hagar. Okay, now I said Hagar splitting, not a Hagar diagram. So now I want to think really as sort of going to forget that the Hagar, we know that comes from Morse theory, right? But now I'm going to write M as equal to a, I'm going to say A union B, and A and B are both diffeomorphic to solid G handle bodies. And they're glued together by some map phi, which is a map from the boundary of B to boundary of A. Are you happy with that? So now, what I want to do is remember that also S3 can be written as A union B with some other gluing map C. So why is that? Well, one way to say it is I could take the standard, well, what's the easiest way? The easiest way to see it is I take a Morse function S3 with just a single index 0 and a single index 3 critical point. So that corresponds to a genus 0 Hagerite splitting, just two balls. And now I just stabilize it. I add a whole bunch of do a whole bunch of 1-2 births until I get to genus G, and now I've got a genus G splitting in S3. Okay. And so now I want to compare. So what I want to do is compare these two splittings. So one way to think about M, so this is just a schematic, you know. So to make M from S3, what you do is you start with S3, and here's A and B, and let's call the splitting surface, let's say it's sigma G down to A, and sigma G, and then cut, right? Cut open. And then you reglue. That's all I'm saying. And what I want to do is think of regluing by, and then rather than say reglue by phi, like we should really properly should say reglue by phi composed of C inverse or something like that. It doesn't even really matter to get that exactly right. So I won't really write it down, but and then reglue. I mean, it all depends on what's parameterized and what. Reglue, maybe by the C inverse, something like that. That's probably the way I can say it. That doesn't matter. When you get back, you've still got A and B, but you've reglued somehow. So now this is equal. Yeah. Okay, that's just nothing, no big deal. They cut it apart. It's got one gluing map this way, you cut it open, and you glue it differently. But the point is, now what I want to do is use a theorem that says, so let's just call this, whatever this new gluing map is, call that, let's call it F, H. Okay. And so I'm just going to think of H as a map from the surface to itself. And all that matters is H up to isotopy. Okay, that's one thing we said earlier. If you glue manifolds together along their boundary, the only thing that's important is the isotopy class of the gluing. So, so we really think of the equivalence class of H in the mapping class group of sigma G, which that is diffeomorphisms from sigma G to itself, modulo isotopy. I should really, right. These are orientation preserving diffeomorphisms if you orient things appropriately. Okay. And then I'm going to use a theorem which is proved, which I'm not going to prove, but is in that licorice paper, which is that this is generated by Dane twists. But I'll tell you what Dane twists are. So Dane twist is you take a maybe you probably already know, but just clear. So Dane twist is an automorphism of the surface determined by a simple closed curve in the surface. And so, Dane twist, right, tau C. C is a curve in sigma. So I may have to use lots of different curves. So if I have a, I'm going to draw it this way. I think it's a, automorphism of the surface that's supported in the side of neighborhood. So if I'm going to draw a copy of this, so this is an angular neighborhood curve. C. An important feature of the stain twist is what it does to arcs cutting across this annulus transversely. If I take an arc like that, then it would go so that's it. So it's often drawn this way, but I have a reason for wanting to draw it that way. So another reasonable way to draw it is to draw the neighborhood of the curve as a cylinder, and then say that this goes to that. So then you think you cut open along the cylinder and twist. Okay? But look at this cut open along the cylinder and twist. What I want to do is now think about cutting this 3-manifold open along this curve and applying a Dane along the neighborhood of the curve and applying a Dane twist. So, so let's factor as okay. So by the way, the proof that every map and class group, the map and class group is generated by Dane twists. That means that H is isotopic to a composition of Dane twists, and the proof of that is really quite nice and elementary and worth reading. It's just not Morse theory, so I won't do it. It takes about a lecture. Okay, but so H, H is isotopic to twist along curve Cn, twist along Cn-1, twist along C1. So I want to think about those. These are different curves. C1. Okay, so those are curves in the surface. So what I want to do now instead is make a slightly different schematic, and I want to build M piece by piece. Okay. So instead, what I'm going to do is take. So now I take step by step. And so what I'm going to do is take a, I'm going to think of first start with S3, and I'm going to cut it into A and B, and then here I'm going to make a whole lot of slices. Except I'm only going to slice across them one at a time. So each of these slices is going to be, each of these slices is sigma g cross 0, 1. And there are n of them. So cut open along the first one. Okay, so cut and then let's see where I'm going here, and then glue here, glue with tau C1, etc. So I'll glue with tau C1, I get some intermediate manifold. It's not S3 anymore, and then I'll cut here, and then cut and glue with tau C2, etc. Or you could say you could cut all at once all these slices and glue the bottom, glue here with tau C1, then here with tau C2, and so on. And you're stacking them all together, and that corresponds precisely to the composition of these things. So that, I mean, that does take a little bit of thinking, and again, but I think you get the idea that you just stack these curves one by one. And so now I want to finally, now I have time. So next time what I'm going to show you is that cutting open along a single surface, and there's a curve in the surface. You cut the 3-manifold open along the surface, there's a curve in there, and then re-gluing by a Dane twist along that curve. First of all, that's something that happens just in the neighborhood of that curve, right? And what you're really doing is you can think of it as sort of, the way I think of it is sort of blister the manifold open along this curve, and then you glue again. When you blister it open, you're really removing a solid torus. And when you glue it back in, you're putting a solid torus back in, but you're putting it back in with a twist. And that's going to be the surgery. So this is going to correspond to the surgery once we show that, we're going to show that every 3-manifold can be gotten from S3 by doing surgeries along circles, and those surgeries will correspond to handle attachments for the formula.